Today we're going to go through section 2.4.1. We're going to be dealing with square roots and cube root functions. If you turn to your notebook, there should be a blank page right around page 90. If you want, we're going to actually have the same setup for 4 different slides. So if you want to copy this down, we have our graph, domain, range, increasing, decreasing. We're also going to have a new function on each page and a small table. So if you want to take the time right now, you can hit pause or just pause when we get to each problem, but we're going to do 4 of these slides. So let's look at the first one. This is our basic parent square root function. F of x equals the square root of x. And anytime you're introduced to a new function, the most basic way to decide what that graph looks like is to do a table of values. Remember, a graph is just an infinite number of points of input and output. So that's what we're going to do. But when we're doing input and output, we don't want to just pick any random number. You want to pick something that makes sense for the problem. So for example, if we're taking the square root of x, excuse me, it doesn't make sense to put a 5 in there because the square root of 5 isn't nice, but we can pick nice numbers. For example, the square root of 4 is nice. Square root of 4 would be 2. I could pick 9 would be 3. The square root of 1 is 1. Even the square root of 0 is 0. So I'm going to plot some of these points. So, excuse me, 4, 2, 9, 3, 1, 1, and 0, 0. So that gives us kind of an idea, rough idea of the curve that we have here. Okay, but I only picked positive numbers right now. What happens if I pick, for example, a negative 1? If you guys remember from one of our first chapters, the square root of negative 1 is just I. And because this is just our xy plane, it's not a complex plane, I can't graph that. So anything in the negatives actually is undefined for this problem because we would not be able to see it on a real graph. So what I'm going to do is I know, if I put a 16 in here, I get 4, a 25, I get 5. So this is our basic shape for the square root function. Okay, we have nothing back here because it's all undefined. If you were to type this in your calculator, we'd just see error for all of these values. And it's going to continue on with this kind of curve going on forever. So what we're going to do is we're going to try to answer these 4 main questions. Domain are our x values. So if we look at this, the furthest left we go is 0. And then this graph keeps continuing right forever, so we're going to go all the way to infinity. We can never equal infinity, so we use a parenthesis, but we can equal 0, so I'm going to use a bracket. Range are our y values, so again, we always start low. So the furthest down our graph goes is 0. And then this graph will continue up forever, slowly, but will continue up forever. So we're going to put an infinity here. And again, parentheses and bracket. Now increasing and decreasing. Just make sure you go left to right. So if we go left to right, my y values are always getting larger. There's actually never a time where we come back down like a parabola. So this is increasing, always increasing, right? So this is always increasing right now for this picture. And when do we start increasing? We start at 0 because this is undefined. And when do we stop? At infinity. But remember, increasing and decreasing, we never use brackets because at 0, we're not doing anything. Okay? Decreasing, never. Okay? It doesn't even exist. Okay? So this is our basic square root function. And again, if you forget what it looks like, you can always just put square root of x and start substituting in values to get this basic shape. So again, we have our domain, range, increasing and decreasing. Now, we don't have a starting point, but this point right here, okay, we call our critical point. So for this problem, our critical point happens to be 0, 0. And that's going to be something important that we talk about in each of our problems. So again, we'll call it a critical point. It's basically our starting value for our square root function. So let's go on to another example. This one looks quite a bit more complicated. I've added in 3 more numbers. If you notice, this one is not underneath the radical, and we know that because the line does not extend over it, so just make sure you take note of that. But we're going to do the same exact thing. If I don't know what something looks like, I'm just going to pick values. But I'm going to try to pick values that make sense. So in the last problem, we put in a 0. Let's see if 0 makes sense. Well, 0 plus 4 is 4, and the square root of 4 is nice. So I'm going to use 0 as one of my numbers. The square root of 4 is 2. 2 times negative 2 is negative 4. Negative 4 plus 1 is negative 3. Last time I used a 1, but 1 plus 4 is 5, so that one doesn't work out really nice. So if I want to try to think of other nice square roots, if I put a 5 in here, I'm going to get the square root of 9, which is 3. 3 times negative 2 is negative 6. Negative 6 plus 1 is negative 5, so I know that number works out pretty nice. The last time we actually didn't use any negative numbers, but let's think if a negative number works here. If I put a negative 1 in here, for example, I actually get negative 1 plus 4, which is 3, which we could take the square root of 3. So because of this adding 4, I actually have the ability to put in some negative numbers. And I'm actually going to go all the way down to negative 4, because negative 4 plus 4 is 0. The square root of 0 is 0. 0 times anything is 0, so I'm going to get a 1. And I can actually put in that 1. And even if I put in a, let's say, a negative 3, negative 3 plus 4 is 1. Square root of 1 is 1 times negative 2 is negative 2. Negative 2 plus 1 is negative 1. So what I'm going to do is going to take some time to graph these values. And see what this shape looks like. So 0, negative 3, 5, negative 5, negative 4, positive 1, negative 3, negative 1. So let's kind of think about what this shape looks like. Did I pick the right numbers? Well, what if I tried to pick anything smaller than negative 4? So let's say I put a negative 5 in here. Well, if I put a negative 5 in here, I'm going to get negative 2 times the square root of negative 1 plus 1. So this is going to be imaginary. So anything I go less than this, if I pick any number smaller than negative 5, I'm actually going to get errors all over here. But if I pick more positive numbers, I'm completely fine going to the right. So this is kind of going to be what our shape of our graph looks like. And it's going to keep going to the right forever. Now in this problem, this happens to be our critical point. Our critical point was right here at negative 4, 1. It's our critical point. Okay, we're going to talk a little bit more about that in a second. So let's go through and see if we can answer some of these questions. Domain. Well, domain X, the furthest left we go is negative 4, and we can equal negative 4, and then this graph goes to the right forever. Range. Okay, so this is where a lot of people mess up range. We always have to do smaller number, bigger number. So what's the furthest down my graph goes? Well, this graph keeps going down slowly. So negative infinity is the lowest my graph goes, and the highest it gets is positive 1. Now, excuse me. The last example we did was always increasing, but if we look at this one, our y values keep going down, 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 so we are always decreasing for this one. We actually will never have the y values go back up, so we have never for increasing, or NA, and in decreasing, well, when do we start? Again, we write our x values. We start at negative 4, and then we never stop going to the right, and again, we always use parentheses there. So I want to come back to this critical point. Negative 4, 1. Where could we just look at that and see? Is there a way that we could tell what the critical point is without having to do all of this guess and check work? And we have this 4 and this 1 here. Now, if you think about what we've done previously with quadratics, this should look very familiar. Okay, this should look very similar to our vertex form. Okay, we have this value in front, which is like our a value, and then we did the opposite of this number right here with the x, and then we kept the outside number, which is exactly like our h and k from our vertex form. And that's the form that we're going to use for the square root function. We have y equals, or f of x equals, a times the square root of, again, x minus h plus k, where x minus h is underneath the radical. So now it makes it a little bit easier. If we go back to our last example, our critical point was at 0, 0. Well, why was that? Well, if I look at this, I had an a value of 1, square root x minus 0, I didn't take anything, and then plus 0. So that's where our critical point ends up matching up the exact same way. So I could throw any problem at you, and you should be able to come up with that critical point. Now, what did we do from there on? Well, kind of going through here, there's a couple of things that we can use to help us graph this. One is that a value. If you notice in our first problem, we had a positive a value, and our graph was increasing or going up. In this example, we have a negative a value, and it goes down. It's always decreasing. Very similar to what we did with our quadratics, looking at what the a value does, helping us know which way it opens. Positive, it's going to go up. Negative, this one's going to go down. Okay. Now, how do we get this pattern? Well, actually, if you turn your head kind of to the side, all our square root function is, and we'll spend more time evaluating this as we go to further sections, but all this is a half of a parabola. Okay? So, if you guys remember when we briefly did it with our quadratics, I'm going to show you here. If you remember when we had our quadratic function, we had these points and we went right 1, up 1, right 1, up 3 for our values. Or if you want to think of it more as a square root function, or sorry, quadratic, 1 squared is 1. 2 squared is 4. How do we get to the next point? 3, I square 3, I'm going to go up 9. And that's where our points come from to get our curve. Okay? We just go back to this parent function. If I put in a 1, I get 1. If I go 2, I get 4. If I go put in a 3, I get 9. If I put in a 4, I go 16. But it all is how much we move from this vertex. It's the same idea here with our square root function, but we're going sideways now. Okay. Now this was a 2. Okay. So what happened is every time I moved 2 over, I went up 1. Okay, so I'm doubling my value. So instead of going over 1, up 1, now I'm going 2 down over 1. Okay, then I went 4, and then I went over 4. Okay, so the output is staying the same. I'm still going over 1, over 4, over 9. I'll go over 16. But because we're kind of turning, I'm doubling how many spaces I'm moving up and down. So this is going 2, then 4, then 6. Okay, I'm changing my 1, and then my 3, and my 5. Okay, so we'll do extra practice with this, but if you get stuck, you can always do just a table of values, and that's what I suggest doing at the very beginning instead of trying to remember some random pattern. Go back to basics and think, okay, I know where my critical point is, I know which way it faces, and then just pick points past that. Right? I picked a -3. I can pick a 0. Pick numbers that make this work out nicely, and it's very easy to graph. But some people use a pattern of the a value, but you can always go back to substitution. So that's our very basic square root function. We're going to follow a similar pattern with our cube root function. So again, we're going to do 2 slides like this. Okay, what changed? Instead of a square root, we have a little 3 here. This is called the cube root function. So like anything else, if we don't know what something looks like, we're going to just pick a different value, substitute it in, and see. So now we want to find numbers that have a perfect cube. So that means we can break it down to, for example, 8 is a perfect cube because it's 2 times 2 times 2. Okay? 1 is a perfect cube. 1 times 1 times 1. 0 works. 0 times 0 times 0. So right now, I know 0 works. 1, 2, 3. Go up to 8. 8, 2 worked. And 1, 1 worked. Okay, so those are some positive numbers. The next perfect cubed in the positive would be 27, which is 3 times 3 times 3. I definitely want to go out that far. But let's see if negative would work. What about -1? I know when we took the square roots, the square root of -1 was was an imaginary number, but what about the cube root? Okay, if we take the cube root of -1, are there 3 numbers that multiply to give you -1? Well, -1, -1, -1. So the cube root of negative 1 is just negative 1. Okay. Well, let's try our next one. What about negative 8? Well, that would be negative 2 times a negative 2 times a negative 2. So let's plot a couple of these points and see if we can kind of see what our shape is. Now, this is going to keep going out really far to the right and only up a little bit, so it's going to grow very slow that direction. And then same thing here. It looks like a little snake going through, going from left to right. Okay. So let's see if we can answer some of these questions down here below. What is the domain? Well, what's the furthest left this graph goes? If I follow this arrow, I'm going to go all the way to negative infinity. And if I follow it all the way to right, I'm going to go all the way to positive infinity. And since we can't equal infinity, I'm just going to put parentheses there. Try to get some of these boxes off. Okay. If we go for range, now it's hard to tell, but this graph will slowly go down and down because if I pick another bigger number, I'm going to get a bigger, or in this case, a negative output that's smaller than this number. If I put in 27, I'm going to get a 3. If I put in a 64, I'm going to get a 4. So this is slowly going to go to the right. So even though it's hard to tell, this does go down forever and then up forever, both with parentheses. Now let's look at increasing and decreasing. Just like before, make sure you read left to right. So if I start at the left, my hand or my Y values are getting larger, and they keep getting larger all the way. So this actually, if we think about it, is always increasing. So we're going to start at negative infinity, end at positive infinity, and this will never decrease. Okay. So that's how we answer some of the key things here. Now, there is no real, if we talk about a critical point, the point might be right here. Okay. You'll talk about where this turns, this is concave, what we call concave up, and switches to concave down. In calculus, we'll spend a lot more time with these, what we call inflection points. But this is our critical point for us right now, right here at 0, 0. That point where we change our concavity, how we curve. Kind of openings up, and then it opens down. So let's look at a more complicated example. So again, just like I did before, here's my cube root of x right here, but then I added these other 3 numbers. So just like before, let's try to pick numbers that give us perfect cubes. I know 0 was a perfect cube, so if I put in a 2, I'm going to get the cube root of 0, which is 0. Anything times 0 is 0, so it gives me a negative 3. I remember 1 was a perfect cube, so to get that, I'm going to put a 3 in. 3 minus 2 is 1. Cube root of 1 is 1, times negative 1 half is negative 1 half, minus 3 would be negative 3 and a half. Okay. 8 worked, so to get this to be an 8, I'm going to put in a positive 10. Cube root of 8 is 2. 2 times negative 1 half is negative 1. Negative 1 and negative 3 is a negative 4. So let me use those for the positive side. Does not want to work today. Okay. Let's get some of these points on here. So we have 2, negative 3, 3, negative 3.5, and 10, negative 4. Okay, so let's see if I substitute in some different numbers. So this gave me my 0, my 1, and my 8. Those are some of my perfect cubes, but let's go in the negative direction. Negative 1 worked. So to get a negative 1, I could put in a 1. Cube root of negative 1 is negative 1. Negative 1 times negative 1 half is positive 1 half. A half minus 3 is negative 2.5. 8 worked. So to get, negative 8 worked. So to get a negative 8, I'm going to put in a negative 6. Cube root of negative 8 is negative 2. Negative 2 times a negative 1 half is a positive 1. 1 minus 3 is negative 2. So let's plot a couple more of these points. All right. So 1, negative 2.5, and then negative 6, and negative 2. Okay. So hopefully you can see that similar shape we had on the last page. So we're going to come here, it's going to curve through here, and then go that direction. So in this example, our critical point is right here. Let's see if I can circle it for you. Okay. It ends up being our 2, -3. And hopefully you can see from what we did the last time that 2, -3 comes right from here. I see this x minus 2, which happens to be underneath the radical, and a minus 3. So, just like we did before, okay, we have this form, y equals a, there's our a value, the cube root of x minus h, and then plus k, which is very similar to our vertex form. So again, this would be our critical point, or what would look like our vertex from before. The opposite of -2 gives us a +2, again, because we have a subtraction, and then we just write our -3. Okay, so let's start to fill in some of this information. Domain, well, again, it goes left forever and right forever. Okay. Range, well, this slowly will go up forever, slowly go down forever. We always do the smaller number first. Okay. Increasing and decreasing, well, if I move left to right, actually my y values are always getting smaller. Okay, so if we go this direction, which you have to go, we are always decreasing. So we start at -infinity, we end at +infinity. And this one never increases. Okay, so if you compare what we did in the last problem, with our parent function, when we didn't add all this, we had an a value of 1, and it was always increasing. As soon as I make that a value negative, we're always decreasing. The nice thing about our cube root function is there are no domain restrictions. We don't get any undefined, so we literally go -infinity to +infinity for all parts. Just figuring out that critical. Our critical point again is 2, -3. And if you notice, we get this symmetry. Okay, how much we move from this point to the points on the left of it and the points to the right of it are the exact same. We just have to decide if we're going up to the right because we're increasing, because a is positive, or if we're going down as we move to the right, if our a value is negative because we are decreasing. Okay. So we're going to use this. You're going to be expected to be able to do an accurate graph like I did with points, find the domain range, and when it's increasing and decreasing. So let's look at a couple of the examples actually in the book. So on page 93, okay, I'm just going to talk to you about how they ask a couple of these questions to make sure you're okay with your homework. So they give us this function right here, and this is a square root function. And what I would expect you to be able to do is to look at this and be able to pick out some key points. So right now, if I look at this, I should be able to figure out the critical point is -30, comma, and I'm not adding anything, 0. Okay, so my critical point is -30, comma, 0. Okay. I should see that my a value is positive, so this is my square root function, so it should look like that. It should go up. Those are some of the key things I would think you should be able to pick out. Determine the range of the function, then use the graph to estimate the value when y equals -10. We're just going to talk about a couple of these points. But what they're telling us is that this is a domain, if I was to write out in our notation, of -30, comma, 0. Okay, well, we know that this graph normally goes on forever, but they are choosing to restrict the domain for us. They don't tell us why, but they're restricting it. So how would we figure out the range? Well, remember, domain is the x, range is the y. So right now, I know that when x is -30, I get a y value of 0. Okay? But what happens when x is 0? Okay? Well, if I substitute 0 into this equation, okay, show you what we get here, I'm going to get 0.176 times the square root. If I put in 0, I'm going to do the square root of 30. I get 0.96. Okay, so what I have here, okay, is that these are the x values. If I look at the y values, when x is -30, I get a y of 0. When x is 0, I get a y of 0.96. So this would be my range. My range is just 0 to 0.96. We can literally just use the starting at any value for x and find our starting at any value for y. So this just says find at least 3 points on the function. How would you find 3 points, including the critical point? Well, our critical point was that -30, 0. I found a new point at 0.96. Just substitute any other value, and you should be able to figure out a third point. I chose to substitute in a negative 15 halfway. So if I asked you to graph this, all you would do is just pick points. You can use the ones I did, and then you would just slowly try to graph that. Okay. Now I'm not going to put arrows on this because they told me that we start at negative 30 and we end at 0, so I cannot go further than that. Okay. If you wanted to figure out, it says find the value of y when x is negative 10. Well, just substitute a negative 10 into your equation and solve from there. Okay, so you might have a problem that looks like that. Your next problem is going to ask you to compare. Now, the book just asks for domain, range, and the graph, and the critical values, but just make sure you'd be able to answer increasing and decreasing as well. So I'm going to do our parent one in red, and I'm going to do this new one in blue, and just show you quickly what we would expect. This is a cube root. Okay, so I hope you know that looks like the snake. It's got an a value that's 1, so that tells me, okay, I have this little snake, but it's always increasing. So drawing a light sketch will be helpful. The domain would be negative infinity to positive infinity. It goes left and right forever. The range, well, goes down forever and up forever. That doesn't change. And the critical point, if I look at where that h and k would have been, my critical point would have been at 0, 0. I'm going to come over here. Again, I have a cube root, so that's the snake, but it's a negative a value, which lets me know it's always decreasing. Okay? Now, just be careful. This 2 is not underneath the radical. Okay? Because it's a cube root, the domain and range, unless told otherwise, will always be negative infinity to positive infinity. This, if you look at it closely, this is x minus 0 and then a plus 2 out here. So my critical point would be 0, 2. If I asked about increasing and decreasing, this one would never decrease and always increase. This one would always decrease and never increase. So they might give you a cube root or a square root function for that. The last problem is just really wordy. It looks scary because of how much extra information they give you. But basically we have this pool, and they're giving us the dimensions in terms of d. So we have a depth of d, a width of 2d, and maybe this length of 4d. And they pretty much do all the math for you. They're saying that the volume of a pool you get by doing length times width times height. But then they converted this equation for volume and solved it for d instead of v. So if I get rid of all this extra stuff, d is equal to 1/2 times the cube root of v. And what they're asking for you in this equation is they're telling you that they would like a pool with a volume of at least 1,000 and no more than 11,000. So what they're telling us is that the volume can be 1,000 all the way up to 11,000. Okay? Okay? And since that is where the x would be, this is our domain or our input. Okay? So they want to know what are all the possible values for d. Well, since d is where y is, that's our output or our range. So that's really all they're asking is what is the range for this? So to figure out the range, okay, I'm just going to substitute this value in. I'm going to substitute in 1,000 and get an answer, and then I'm going to substitute in 11,000 and get my second answer. So let's do that right now. 1/2, 0.5. Now to get to the cube root easily, you can just go to the math button, and it's the fourth option. Okay, and I'm just going to put in 1,000, and we get a 5. Okay, so our smallest d value would be 5. 5 would give us a volume of 1,000. Let's figure out what happens if we do the same thing. Now, if you have a newer calculator, you can just hit up. I have an older one, so I'm going to hit second enter to replace that. And I'm just going to add in 11,000, hit enter, and it gives me about 11, look at this, 11.12. And then that would be the possible values for d, which technically is our range. Okay. So when you guys go to do your homework today, it's going to ask you to create a graph of the function. You want it to be semi-accurate, so you want to be able to put a few points on it. It should always see the critical point and a couple extra. I should see the domain range, and then also answer increasing and decreasing. It won't be in the back of the book, but you will be expected to do that on your quiz. So hopefully you have a little bit better understanding of square root and cube roots, and I'll be back tomorrow to help you out with any questions that you have.